Okay, so this is going to be a quick review of two derivatives that you're given in the formula booklet, but as a higher level student, you should be able to explain how they come about using these basic rules of differentiation, these basic derivatives that are already available for standard level students, okay? And the functions, the two functions I want to discuss today briefly are this one and this one. So without looking at what the derivatives of these two are, according to the formula booklet, let's try and justify what they should look like based on these basic functions, these basic derivatives, and the rules that we should all be familiar with and comfortable using. Okay, the first one is an exponential, but with an arbitrary base. Yeah, so not base e, but an arbitrary base. So this is pretty much the same type of function as this one, except this one is special. Yeah, so e to the power of x was defined as a function whose derivative is equal to the value of the function at a given time. Yeah, this is the sort of how number e, the Euler's number, was defined. If I do e to the power of x, the rate of change of e to the power of x equals the value of e to the power of x for a given x. Okay, it's nothing but the statement of this thing. And we're going to use this, right? So what we're trying to do basically is convert this into a function of this form. So e to the power of x, right? So in other words, I don't want to have an a, an arbitrary number here. I want to have an e, or the Euler's number here as the base. And I know I can do that because I know I can change, just how I can change the basis of logarithms. I can change the base of the exponent in a very similar manner. How am I going to do that? I just need to write a, so let's use a different color for this. I just need to find an expression for a, this guy here, in terms of e to the power of something. And I'm just going to give it here. And for some of you, it might be obvious why that is. If not, just think about it for a second. So why is this true? Well, the natural logarithm of a is the answer to the question, what power do I need to take the number e to in order to get a? What power do I need to bring number e to in order to get a? And I'm literally bringing e to this power right now. So I'm getting a out, okay? So sometimes just say it out loud and it might become clearer, yeah? So pause and make sure you understand why this is true, okay? And now that we know this, let me just continue and rewrite this function f, as e to the power of natural logarithm of a, which is just a, and now take this to the power of x, right? What happens here? Well, we just multiply the exponents, rules of indices, right? And this is very good. Let me just put this in brackets here to make sure you realize that this is just a constant. This here is just a constant. Otherwise, this is e to the power of x, except the x is multiplied by some constant. So we're just going to use simple chain rule to differentiate this now. So d dx, so the derivative of f of x, so I can write it like that, or I could use the prime notation, yeah? It's going to be, well, how do I differentiate e to the power of something? Well, it stays the same, right? That's the definition of this function, right? First thing I'm doing, I'm just rewriting the same function again. But now, because the exponent wasn't just x, it was x multiplied by a constant, well, I need to use chain rule and multiply by the derivative of this exponent, right? It's a composite function, if you want to call it like that, okay? What is the derivative of x times a constant? Well, it's the constant, basically. So all I need to do is multiply by ln a. And now if you look back at the formula booklet, you'll probably see that that's not exactly the same form that we're given in the formula booklet, which is fine. We just need to do one more thing in order to arrive at that one. We use the same thing that we used here in order to change a into something like this, but we're just doing it in reverse now. Yeah, so I can take this and write it again as, well, just for clarity, yeah, I can just rewrite it like this again and get a back again, right? So in other words, it's just a to the power of x now, yeah, this thing. So it's a to the power of x times natural log of a, all right? Okay, whichever way you'd like to write it is fine. So now the second function is the function g here. It's the inverse sine of x. Yeah, arc sine, same thing as sine to the power of -1, right? Inverse sine. But for this, we will need to use implicit differentiation. And now, if you haven't done it yet, don't worry. Let's just try and follow what I'm doing here. If you have, it should be straightforward. Okay. I've called this function g. Let me just say that this is some y equals arc sine of x. And now I do not know, let's assume I do not know the derivative of arc sine, right? Of inverse trigonometric functions, because I told you that the only derivatives that we need for the sake of this video are basically these ones. In either case, we're using the standard level derivatives to get out the derivative of arc sine. How do we do that? So I told you we're just going to be using these default simple functions, right? I don't know the derivative of arc sine, so I can't just differentiate straight away. I can't just say dy by dx equals blah, 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 right? I have that in the formula booklet, but we want to find out why that is so, right? So we need to do some tricks. How can I get an expression with, well, sine of x instead of arc sine when I have an equation like this? Think of it as an equation for now, yeah? Well, I can just take the sine of x of both sides of this equation. In other words, this says the same thing as sine of y equals x. Yeah, that's the principle of inverse functions. If I take the inverse of an inverse function, I get back what's inside the function, the argument. Yeah, that's what happened. That's what happened here. Okay, so remember what I'm after, what I'm trying to find is this, g prime of x, which now, because I called g of x, I called it y, I'm basically just trying to find dy dx. Okay, so now remember, taking a derivative is same as any mathematical operation. The important thing in this case in particular is that I just can take the derivative of both sides. I can say that derivative of the left-hand side of the equation with respect to x is the same as the derivative of the right-hand side of the equation with respect to x. So that's what I'm going to do now. Different color because it's important, okay? So I'm just doing d by dx. I'm differentiating both sides of the equation with respect to x. And let's start with the right-hand side because it's simple. What is d dx of x? Just one, yeah? Done. Left-hand side is a bit more tricky because remember y itself is a function of x, okay? It's this, right? This here is a composite function. Yeah, we're doing implicit differentiation now, but I'm just showing you how it works, right? And just like chain rule, basically. This is composite function when the x is the argument. So this is a composite function. So we need to use chain rule in order to differentiate that, basically. That's what this whole implicit differentiation thing is about, just chain rule, basically, right? So if I want to differentiate the sign of some function of x with respect to x, I differentiate the outer function. So the derivative of sine of something is what, cosine of something, of the same thing. But now I need to multiply by the derivative of the thing inside because this is a function of x. Yeah, here I'm not going to say what it is. I'm not going to use the fact that it's arc sine or whatever. I'm just going to say that the derivative of sine of y with respect to x is going to be the derivative of the outer function. So cos y times the derivative of the inside function, which is dy by dx. And I want to leave it like this because I'm actually after this guy. That's what I'm trying to find. Perfect. Because what's happening now, if I want to find this, I'm just going to leave it as the only thing on the left-hand side of the equation. Okay. And now there are several ways we can go from here. But the thing is, I know what y stands for. Obviously, I want to find the derivative of y in terms of x, right? Because y is a function of x. Yeah, I want to find this. So I would like to plug this back in. The problem is, like, how is it going to help me if I plug in an inverse sine into a cosine, right? Not much help. But if you remember your trigonometry, the most important trigonometric identity was the one that tells you can always convert between cos and sine of the same angle. Sounds sophisticated, but I'm basically talking about the Pythagorean identity, okay? So I want to have an expression with sine of y instead of cosine of y. I'm going to get this from here. Just need to get rid of the square, so I'm taking the square root. This is some simple algebraic rearrangements, and that's the expression for cosine of theta. So in our case, cosine of y. So instead of cosine of y, I can write square root of 1 minus sine squared of y. And this is very good because now I'm going to be plugging in this thing into here because that's what y is originally. So dy dx what happens if I put arc sine into sine? These two are inverse functions. If I apply an inverse function on a function, I get back the argument, yeah? So I'm just gonna explicitly write it out here. But you should be able to just see it straight away and write this instead. So this is, remember this is square here, right? So I get an x squared. And now, yeah, so that's our dy dx. That's this expression, right? So we wanted to find the derivative of g of x with respect to x. And what we just found is that it is 1 over root 1 minus x squared. Compare with the formula booklet.